Today I'll be talking about ionizing radiation units. So we know that activity, exposure, absorbed dose, equivalent and effective dose and their units, and it's a little bit of confusing. So just to know a little bit in concept wise. So before that, what is exactly ionizing radiation? So we know that we have ionizing and non-ionizing radiation. In ionizing radiation, we need ions which are important for it to be called as ionizing radiation, because here the ions, either like the directly acting ones, that is electrons, they directly act on the DNA and damage DNA. So that can be, or either the photons indirectly changing the water molecules into those ions. This H plus, OH plus, OH minus, hydroxyl ions or free radicals produced, these are all indirectly acting. So either directly or indirectly acting, we need ions to be, for it to be called as ionizing radiation, and these ions are the ones which damage the DNA. And these ions are important because even in our calculation of radiation units, what we measure is the ion or the ion pairs that are being produced. Now coming to radiation units per se, let's take an example. So first let us consider a telecobalt unit where this is the source. So this is the source, and then this is the air, like between the patient or the phantom or something that we have kept here, a material to measure. Okay, so source, air, water, medium or tissue. Now we know that for source, what do we need? For source, what do we measure? We measure activity. So cobalt, it's activity measure. So any source, we measure the activity. So in the air, what are we measuring is exposure. So here, as the photons are being produced, the photons, and like since air also has atoms, right, so those also will interact with them, and then ion or ion pairs are being produced. So that measurement per cubic centimeter, that volume or area, is measured by exposure. Now activity, as we know, for source, how do we measure activity? Activity is measured by becquerel. Now becquerel is the SI unit which we currently use. Previously we used to use Curie as the SI unit, and we know becquerel is 1 disintegration per second. Now exposure, the unit is coulomb per kg, because that's what we are measuring, coulomb, the ion pairs per that unit mass we are measuring the exposure. So previous unit for exposure was Roentgen. Now coming to water or medium tissue, what we are measuring here is the absorbed dose. So now this absorbed dose is like the quantity of the radiation measurement. So here it is measuring the amount of energy absorbed from the radiation beam per unit mass. So from the radiation beam per unit mass, so this mass that you are taking is 1 kg. So you are measuring that unit mass, that is absorbed dose. Now there is very slight difference between absorbed dose and karma, that is karma is kinetic energy released per unit mass. I can talk about that in a next topic video, so if you want. And the absorbed dose or karma is measured by Gray. Gray is basically joules per kg. So in 1 kg, how much energy is in joules, right? So how much energy is being absorbed, so that is absorbed dose, how much dose is being absorbed. The dose is measured by Gray. Karma by joules per kg. Now the older SI unit was rad. Now coming to equivalent dose. Now absorbed dose for radiation protection, see, this will be for only for 1 kg of the mass that we are seeing, but we are not seeing what kind of radiation here is being used here, either it's alpha, beta, gamma rays, neutrons or electrons. So based on these, that is called radiation weighing factor. All of these have different weighing factors. So based on these, the equivalent dose is calculated. So basically equivalent dose, how is it calculated, is absorbed dose into radiation weighing factor. The current SI unit that we used is Sieverts, or represented as SV, and the previous unit that was used was REM, that is Roentgen equivalent man. So, and what is the radiation weighing factors for each? So, if we come to the radiation weighing factors, so gamma and electron, gamma photons and electrons have one radiation unit factor, and the protons have 5, neutrons have a slightly more, that is 10 to 20 based on the energy levels, and alpha 20. Alpha particles is 20. Now coming to effective dose, what is effective dose? Now here we considered the radiation weighing factor. Now let us consider the tissue factor. So here we are just, if you just take homogeneously water, but in the patient we have various tissues, bone, skin, liver, bone marrow, everything. So the tissue weighing factor also differs. So now the better one is the effective dose, right? So effective dose is measured again in Sievert, because it's the same equivalent dose into tissue weighing factor. Now again the previous one was REM over here also. Now coming to tissue weighing factor, it is different in a little bit of different organs. So bone and skin have 0.01, breast 0.05, bone marrow 0.12, gonad 0.20, and other organs 0.05. Totally it should come to 1. So that was about ionizing radiation. I hope it was simple.